This is Jack Jackson. In this video, we're going to summarize something we've seen in the last few videos here. And we're talking about taking isometries, each type of isometry, and thinking about it as a composition of reflections. And in this table, we summarize the minimum number of and type of reflections that we need in the product to obtain the given isometry. So for an identity, we need to have two reflections, specifically about the same line twice. Or if you want to think of that as zero reflections, just leave it alone. You could do that as well. A translation would be two reflections. This time the reflections need to be both perpendicular to the direction of the translation and half as far apart as the distance traveled. And a rotation is also done by two reflections. There will be about intersecting mirror lines at the center of the rotation and at an angle that's half the angle of the rotation. Of course, a reflection is just a reflection is of a reflection itself, so it only needs one. A glide reflection is the only one that actually requires three reflections. The first two mirrors are perpendicular to the direction of the translation and half as far apart as the distance translated. And that's followed by a third reflection around a third mirror that's perpendicular to the first two. Notice that an identity, a translation, a rotation are uh, require an even number of reflections, whereas a reflection, a glide reflection, require an odd number of reflections. This turns out to be an important point. Uh, we can obtain translations, for example, with more than two reflections, but it will definitely always be an even number, 2, 4, 6, 8, something like that. The same is true for the identity and the rotation. But the reflections and glide reflections will always require an odd number of reflections, excuse me. So it turns out that this breaks these into two types of isometries. An odd isometry is defined to be an isometry that can be decomposed into a composition of an odd number of reflections. And an even isometry is an isometry that can be decomposed into a composition of an even number of reflections. And it always turns out that it's always an even or always an odd number. Notice that although isometries are functions, odd isometries are typically not odd functions, and even isometries are typically not even functions. So those even and odd adjectives mean different things whether they're applied to the word isometry or to the word function. So a proposition that we have is that the identity, transformation, translations, rotations are even isometries, and reflection and glide reflections are odd isometries. If any even number of reflections are composed, the result is the identity, transformation, or translation, or rotation. The identity, these three types, can be physically obtained without removing the figure from the plane. The identity, transformation, translation, and rotations produce a non-flipped orientation for the image. Any composition of isometries that produce a non-flipped orientation for the image will have an even number of reflections or combination of reflections and glide reflections. These non-flipped congruent images can be obtained only using only the identity, transformation, translations, and rotations, so that these three form a closed system. Now, for the odd isometries, if any odd number of reflections are composed, then the result's either reflection or glide reflection. They require the figure to move out of the plane into the third dimension in order to physically perform the transformation. Notice that reflections and glide reflections produce an image that is in flipped orientation from the pre-image. Any composition of isometries that produce an image with a flipped orientation will have an odd number of reflections or glide reflections. Notice in our previous work we have shown that any isometry can be obtained from the composition of three or fewer reflections, and we have seen that any composition of three or fewer reflections must result in a single identity, transformation, reflection, translation, rotation, or glide reflection. Together, these results prove that every isometry is exactly one of these five types of isometries. Next, we will look into exploring different compositions of two isometries and look at some details there.